Hello students, for a change, today we will discuss an electrostatic question which was asked few years back in JEE Main exam. One of you have asked this question by writing an email to me, and it is just a coincidence that just few days back, few of my students were also inquiring about this question. So I thought that yes, this question deserves a simple discussion or some treatment because many students find it to be very confusing. Don't get worried, though the question has been asked in JEE Main, but it is a very good question, conceptually very, very, very good question. And we should not always be in habit of branding or labeling a question as JEE Main question or JEE Advanced question. Who are we to do so? Uh, Ultimately, you have to learn this subject. If a question sounds interesting, try it. How does it matter which exam it could be asked in? It doesn't matter. I am saying this because few days back I posted a video and one of you put a remark on that this question seems to be very easy. How can you brand it as JEE Advanced question? Oh my God. Who told you that easy questions are not asked in JEE Advanced? And that particular question was actually a question asked in IIT JEE. Okay, let us come back to our business. Here is the question. There is a metal shell. This blue part is metal, right? Metal shell, this is the cavity region, white one, and outside also there is nothing. That means here it is air, here it is air. This blue part is metal. So it is a hollow spherical shell with some thickness, okay? And this shell has been given a charge capital Q. This shell has been given an external charge capital Q. From outside, we have placed some charge capital Q on it. And there is a short electric dipole at the center of the cell. There is a short electric dipole represented by its dipole moment vector P placed at the center of the cell. So it was a theoretical question, and four theoretical options were given. You were supposed to pick up the most correct one. So the most intriguing one or the most disturbing one was this option. Uh, One of the options said that if we are supposed to write electric field at a point like this, at a point outside this cell, shall we write the field at this point as field produced by a point charge q kept at the center of the shell? If you have been asked to write electric field at a point like this, will you do it like this? Will you say that the field is kq by r square, where q is charge on the shell? That means you are assuming that this charge q is kept at the center of the cell and you are standing at a distance r from that particular charge. So just by assuming that there is a point charge at the center, can you write electric field at this point? Let me first answer this question. Yes, the answer is yes, but it needs a bit of discussion. There are many important points which will come out of this discussion. So stay with me in the video. Don't be in a hurry to skip because you know the answer. Let me tell you what I want you to know, right? So be patient. Be patient. Whenever you are on this channel watching my videos, be a little bit patient. I cannot speak in habad tabad and tell you many facts in minutes. That does not benefit you actually. So let us have a good discussion around the concept actually. Suppose this is any odd shaped metal block having a cavity. Well, I have made a spherical cavity. It need not be spherical cavity actually, but this is the cavity region, and this thing, the colored part, is metal actually, right? And there is a point charge placed inside the cavity, anywhere inside the cavity. All of you, I think, must be knowing that this positive charge, if it is a positive charge, it will attract it will attract electrons on the metal and electrons will get induced on the inner wall. If this charge were at the center of the spherical cavity, then the induced charge will appear uniformly. There is no reason why there will be high charge density here and low charge density here if this charge is at the center of the cavity. But assuming that this charge is not at the center of the cavity, there is every reason to assume that charge density will not be uniform. For example, if this is a positive charge, at nearby locations at these points, a large number of electrons will get attracted and get accumulated. So there will be large negative charge density on this surface, whereas on other parts of the surface, the charge density may not be so large. So the charge distributed on this surface is not exactly, what do you call it? It's not exactly uniform, right? But one thing is certain, that if this charge is Q, then the charge over here is definitely minus Q. How do I know that? You can argue this in many ways, and one simple way is to argue it using Gauss law. If you consider a Gaussian surface like this, I'm so sorry, it's not changing color. Okay. If you consider a Gaussian surface like this running through the metal, this yellow dotted surface is a Gaussian surface which is running through the metal, which means uh, at every point on this surface, the electric field is necessarily zero. Here it is zero, here it is zero, here it is zero, here it is zero, 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 zero. So the flux through this surface is zero, which means the total charge inside this yellow dotted surface should be zero. So if it is a plus Q charge over here, it has to be minus Q charge appearing on the wall of the cavity. But again, let me make it very clear, if the charge is not at the center of the cavity, and for that matter, if the cavity is not the spherical itself, then charge density may not be uniform, but still the total charge remains minus Q, induced charge. Now, think of a situation like this. Suppose, forget about metals, etc. Just forget about any metal or anything. Suppose by some means I am able to create a charge distribution which resembles this charge distribution. What I am saying is, suppose by some tape or something, I am able to fix a point charge over here. Okay, I have fixed a point charge Q, and now the manner in which charge is distributed on this surface in the same density, in this exact replica of that charge distribution, I have created here in this space. There is no metal, nothing, nothing. By some means, you have just pasted these charges here, and these charges are exact replica of the charge appearing on the inner wall of the cavity. Imagine that for a moment. Just imagine for a moment. So if you can create an exact replica of that charge distribution, do you know what you are going to see? Here, anywhere outside this charge distribution, the electric field will be zero. Many of you tend to believe that somehow field inside the metal is zero, but you don't really understand the actual reason behind it. The beauty of this charge arrangement is, that this point charge is creating some field here. Okay, let us say 10 unit field in this direction. Now this induced negative charge exactly cancels this field at this point. If I take a different point, for example, if I take a point like this, then this positive point charge creates a field in this direction, let us say 15 units. Then the same induced negative charge cancels this field also. That means at this particular point, this induced negative charge will be creating a field of 15 unit in this direction. So it is really very strange that electrons have arranged themselves so beautifully, so nicely on this surface, that if you combine the effect of this charge and this charge, then there is no field anywhere outside this charge distribution. Which means, if you are taking a point like this, does this charge create a field here? Answer is yes. Many students tend to believe that if I ask one simple question, what will be electric field due to this point charge at this point? Many will say there will be no field. Absolutely wrong. This charge will do its job. Yes, this charge is going to create an electric field here, here, anywhere. It's the point charge. It will create electric field in its surrounding at all points. So, does this charge, just to वो diagram गंदा हो गया, for this charge, will it create a field here? Answer is yes. K q by r square, yes. But what about this charge? This charge that is hanging on the surface. It will also create a field here. If this one is creating a field of 15 unit in this direction, then this induced charge is creating same magnitude of field, but in opposite direction. They cancel out, and the field here is 0. And this is not true for this point. This is true for this. All the points outside this cavity region. Great. So such beautiful is the arrangement of charge here on the wall of the cavity. And this thing is highlighted. It gets highlighted by the fact that electric field lines, if you know how to draw electric field lines, then electric field lines originate from a positive charge and they do terminate on negative charge. It is a plus q charge. Field line will originate from here and it will terminate on the negative wall of the cavity. And please try to understand that if you are showing 10 lines originating from this plus q charge, then 10 lines will terminate on minus q charge. If this plus q and this minus q, obviously they have got the same magnitude, which means that if you are showing 10 lines originating from this charge, same 10 number of lines will terminate on the charge that is present on the cavity wall. So what it actually means is any field line that is starting from here, it is getting terminated over here. Termination of field line is a way of saying that termination of these field lines here is a way of saying that the effect of this charge system, when I say charge system, I am talking about this charge plus this charge. So the effect of this charge system is felt in this region only. There is no field line protruding out of this region. There is not a single electric field line that is going like this. So if this charge system does not have any electric field because of it at this point, it simply means this charge system does not create any electric field here. No presence of electric field line implies there is no electric field. So this beautiful charge system, this plus q and the induced charge, it is a closed system, kind of closed system, which creates electric field only in this region. I hope you are with me. Now let us go back to the question. This is a dipole, which means there is a negative charge, there is some negative charge over here, and there is some positive charge over here. Obviously, the two charges are on two sides of the center of the spherical cavity. Because this plus charge is a bit closer to this wall, so there will be some negative charge induced here. This negative charge, it is closer to this wall, so there will be some positive charge. We expect that there will be some charges here and there also, but the important thing to understand is the net charge on this wall of the cavity is 0, because this is a dipole. Net charge is 0. And again, by using Gauss law, that means considering a Gaussian surface like this, just considering a Gaussian surface like this, we know that flux through this Gaussian surface is 0, and if it is 0, net charge inside it should be 0. So here charge on the dipole is 0, so induced charge on this wall should also be 0. But the important thing, as I told you just now, this charge, that means this dipole and this induced charge, it makes a closed system. Field lines originating from here, they will be terminating on the wall, all of them. Field lines originating here, some of them might get like this, some of them will get like this. will be a complex kind of field lines. But whatever it may be, one thing is sure, no field line can exit this region, because here we have metal, and inside metal we don't have any electric field. So there is no electric field line present in the metal. No field line can penetrate through the metal. So the net effect is that this dipole and this induced charge, this forms a closed system. Charges induced on this surface are not uniform. That was also part of the question. That was another option given in the question. The charge here will not be uniform, that is for sure. But this closed system will not be able to create any electric field at this point or this point. Because of this dipole, because of this induced charge, the resultant electric field at all these points has to be zero. So what are we left with? The net induced charge on this wall is 0. There are charges, but total is 0. This shell was given a charge q. So where is this charge q residing? Obviously, this charge q is residing on the outer wall of this cell. Very good. Now, how is this charge q distributed? It is distributed uniformly or non-uniformly? The answer is uniformly. Please try to understand, if you don't have a spherical surface, if you have a surface like this and you place a charge q, then there is no reason to believe that charge density here and here will be same. These two parts of the surfaces are not alike, they are different. Here the radius of curvature is small, here it is flattish, here you have sharp turning, here it is flat kind of surface. So there is some difference in surface. So if there is some difference, then we should be very cautious. We cannot say that charge density over here and here will be same. I guess all of you know this, that charge density here will be much higher than charge density here. But if it is a spherical surface as given in the question, present question, then there is no reason to believe that charge density here, here and here will be different, when this charge distribution is not under influence of any electric field. There is no other nearby charges, and whatever is there inside the shell is having no effect here, right? This is a closed system which does not produce any effect outside this wall. So this charge here on the outer surface does not even know that there is something kept inside the shell. So obviously this is a uniform charge distribution, and if it is a uniform charge distribution, you all have studied that a spherically symmetric, spherically uniform charge distribution can be assumed to be kept as a point charge at the center if you are trying to write field or potential at an outside point. So yes, for writing electric field or potential at this point, we can assume that this whole thing is just a point charge kept at the center of the cell. I don't know how many of you are actually with me till now, but if you are there, I assume that you got benefited a lot. Even if you were knowing this earlier, you must have got a new perspective as far as this system is concerned. See you in the next video. Goodbye.